applications of double integrals. The first one is volume, which is how we define double integrals to begin with. If x squared is greater or equal to 0, then the double integral is the volume. Of the sum between the region and the graph of F. Okay, and I'm going to demonstrate with an example, number 11. Find the volume of the solid, which lies under the graph of x squared plus y squared. And could you please keep quiet? Bounded by y equals 2x. That's a straight line like so. And y equals x squared. That's a parabola like so. Okay, so that's y equals 2x. And this is y equals x squared. Okay? Now that word bounded is important. Okay? The word bounded is important. It means that our region is completely edged by those curves. So let me just go on about that for a bit. Catch up with my stylus. Here we go. Here's a parabola. Here's a straight line. Okay, it's a bit wobbly. But this over here is the only bit that's fully bounded. Question. Could I please go up? All of the other regions, like this one over here, or this bit over here, this bit down here, and all of the other bits, they're not bounded. They go on forever. They don't have edges. So whenever you see that term bounded, it means you're trying to find a region that's completely closed in. Think of those as fences. You're flying over in your helicopter looking to see where you're going to keep your alpacas. You're going to keep them over there, otherwise they're going to wander off. So you're looking for the region that's fully bounded, that's fully fenced in your alpacas or your llamas or your sheep. I'm trying to think of something a little bit more exotic than sheep. Aren't going to wander off. Goats jump over everything, so we can't count goats. Okay. Or rabbits, I'm trying to think of, So bounded means completely bounded, means completely fenced in. Okay, let me rub all of that. That's just a demonstration of what bounded means and what's not bounded. And sometimes it can be confusing which region is being talked about, particularly if there's several curves. Okay. And another thing, sometimes there'll be a third curve in there, bounded by this, that, and the next thing, and you'll have several bounded regions actually, but there'll generally only be one region that's bounded by all three of the curves that have been mentioned. Maybe there'd be some other region on your diagram that's bounded by only two of those curves. So if the description of the problem says bounded by curves 1, 2, and 3, you're wanting to find a region that has all three of those curves as part of its perimeter. That makes sense. But I'm sure we'll encounter more examples along those lines as we go. Okay. So that's my region R over there. I want purple, I want dark blue. There we go. There's my region R. And I want to work out my volume. So the volume is going to be the double integral over R. My integrand is the surface, which is x squared plus y squared. Now I need to set up that double integral. Okay, my integrand doesn't care which variable goes first, x, y. My integrand is symmetric in x and y. And in fact, my region doesn't really either. I'm going to make y go first, simply because my curves are already written with y as the subject. I go from the bottom of the region, which is x squared, to the top of the region, which is 2x, for values of x that go from 0 to 2. You'd have to work out the intersection between those curves. It'll be 2, 4. Oops. A bit wonky. That's y. That's x. Okay, we could have done x first. That would also have been fine. Then we would have read our region from left to right. The left edge of the region is the straight line, y over 2. And the right edge of the region is the parabola. It would be the positive square root of y. For values of y that go from 0 to 4, that would also be fine. The negative square root of y would be the left side of the parabola, which isn't part of our problem. Yes. Okay, so if x is going first, we are interested in reading our region from left to right. So I've drawn a little red strip there. The limit that goes at the bottom of the integral is the left edge of my region, and this that goes at the top is the right edge of my region. So the left edge of my region is the straight line x equals y over 2, and the right edge of my region is x equals square root y, yes? This is the left edge of my region, and this is the right edge of my region. And that's not a function of how I've drawn it. I mean, if you draw y equals x squared, what does y equals x squared look like? Y equals x squared is a parabola that looks like that. Y equals 2x, that looks like that. I mean, I think if I wanted to, it still wouldn't change what's on the left and what's on the right. Yeah. Could you please keep quiet? Okay, it says to find the volume of the solid which lies under the graph of z equals x squared plus y squared. So z equals x squared plus y squared is our surface. And we're wanting the volume underneath it. So z equals x squared plus y squared is a paraboloid that looks like this. Okay. And we're wanting to find the volume underneath that paraboloid. The region that's bounded. So that's two-dimensional picture that I drew. I'm going to transpose onto my three-dimensional picture. Catch up with me, stylus. So that over there is my R. So what I'm basically going to be solving for is, I'm going to be solving for some funny volume over there that's under the paraboloid and over that two-dimensional region. No, I haven't. Well, I'm busy doing the integral over there now, so I haven't finished the problem. So let's have a look. What was the first thing I did? First thing, well, I suppose the first thing I did was write down z equals x squared plus y squared, but that's just me jotting down notes. The first step is draw the diagram. Draw R. Okay. And then the second step is set up the sort of general formula, which you could write that before knowing what R looked like. And then step 3 is set up the limits of integration. And then step 4 is actually do the integral. Solve the integral. So let me just finish that, and then if people have more questions, we can talk about it. Okay, I'm differentiating, I beg your pardon, I'm integrating with respect to y, so I'm asking myself, what did I differentiate with respect to y to get x squared plus y squared? It's x squared y plus 1/3 y cubed. That should be in square brackets. X squared is 2x. Okay, that'll be what? 2x cubed plus 8 over 3x cubed minus 1/3 h to the 6th. Let's round bracket this time. Fix my brackets. Dx, bless you. And then that's a polynomial integral, and no, I'm not going to do it. Turn it into an improper fraction. Yeah.
So if you do your limited integration according to the x, y of the region, and then you just integrate that shape according to that region, you'll get the volume in that
Yes.
region.
Yes. 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 Remember how we define double integrals? Basically, the way we define double integrals is we put a lot of pillars with a rectangle cross section on top of the region, and the height of the pillars is defined by the surface. So each little pillar has a volume of its height times cross-sectional area. The height is the function of x squared plus y squared, and the cross-sectional area is x plus y. So it's summing a bunch of volumes of rectangular prisms, I suppose. And that's what that integral is. That integral is a sum. It's a double sum of volumes of rectangular prisms whose height is represented by the integrand and whose cross-sectional area is represented by the limits of integration. Yeah. A question over there and then at the front. Why do I have 8 of them? I substituted 2x into what's inside the square brackets. So I've got x squared times 2x is 2x cubed, and then I substitute 2x and then cubing it, so it's 8x cubed, this is 8 and 3x cubed. Minus, I'm substituting in the x squared, so it's x squared times x squared. Minus, I'm substituting in x squared, and it's a third x to 6. I think it's correct. Question at the front. Okay, so the question is, if you'd actually use this one on the right over here, where x went first, does it matter? It doesn't matter at all. You'll end up with the same answer. In fact, if you're wanting to give yourself a little bit of practice in double integrals, why don't you leave a bit of a space and actually do that x1 and convince yourself that you do get the same answer. Let me just write one more thing in here. Oops, wrong way. These limits of integration. The limits of integration come from R. Or in another sense, they describe R. The limits of integration are R. Okay. Any more questions on that? Doesn't look like it. Okay, let's move on to some more applications. Let's have a look. Okay, here, area. Just want to quickly check, are we onto any of our flow diagrams yet? That's flux, that's mass, that's work. No, but we almost are. Almost are. Okay, all right, area. Here's an easy one. Please be quiet. Okay, we're going to be doing 3 multiple integrals in this course that have 1 as the integrand. This is the first one. The double integral 1 dA is the area of R. The other 2 that we'll be doing is 2 integral signs, but it's a surface integral, so there'll be an S at the bottom. So the surface integral 1 ds, we'll encounter that Monday probably, is the area of a surface, and triple integral 1 dv will be the volume of a region. So we're going to be doing 3 multiple integrals that have 1 as the integrand. This is the first one. And this I think is fairly easy to see, because if you think of dA as being delta x, delta y, that's what we're summing up. We're summing up a bunch of areas. We're taking all the little delta x times delta y's, in other words, all the delta a's, and we're sticking 2 sigmas in front of it, and we're adding it up over the range of x's and over the range of y's. So there's nothing funny going on here. We're simply summing areas. We're dividing our region into lots of little blocks, working out the area of each little block, and we're adding them all up. That's what that is. So that is the surface area of a lamina in the shape of R. Okay, here's a slightly trickier one, and I'm going to give it to you now without any kind of derivation, because when we get to surface integrals, we will derive it.
Sorry.
Yes. I can hear a voice. Where's the... There, yes?
What's the one representing? The one in front of the DA.
Well, normally you actually wouldn't even write the one. You just write sigma sigma dA. So it's not really representing anything. It's confusing if? Well, you can think of it as one if you want, and then of course your units go a little bit dodgy. But if you have a region that has an area of 10 square units, and then you have something that's 1 unit high all over it, and you want to work out what's the volume of this object now, its volume will be the surface area times the height. So it'll have the same magnitude as, the same number as the area. You would just have it as units cubed. See what I'm saying? So if we're only looking at the number and we're not actually thinking of units, then thinking of that as the volume of something that's 1 unit high is also a legitimate way to think of it. Yeah. Okay, surface area. If a surface S, so like a piece of parabola or a piece of sphere or something, if a surface S is described with some function where the domain of the function is your R, if it's continuous partial derivatives, basically your function is nice and well behaved, then the surface area of F described by, okay, and here's a rather chunky looking formula. Double integral plus x squared plus dz by dy squared dA. Now, I'm not going to go into a lot of detail there, because when we get to surface integrals, we will do this in a lot of detail, so I don't want to repeat myself. There's a couple of ways of looking at this formula, but probably the simplest way of thinking of it is in the background behind this formula is a whole bunch of Pythagoras theorem, where you are... If you think of a piece of surface, some curvy piece of surface that's floating above the ground, and you know how to work out areas of regions that are flat on the ground, you're working out with a double integral, the one that is just there at the top of the screen there. What you can do is you can take your piece of surface and you can project it down onto the xy plane, and you can work out the area of the projection. Except, of course, the area of the projection is not, it's probably not exactly the same as the area of the piece of surface, but they are related. They are related. If yeah, okay. As I say, I don't want to repeat myself. I'll talk about this a lot when we do surface integrals. But if you can think of a piece of paper, something nice and flat and rectangular. Okay, so here's my book. If I'm holding my book like this, a steeper angle or a shallower angle, so the shadow of the ground also is much on the ground is different. So there's a relationship between the area of the angle and that it's at and its projection onto the ground. And in one way, you can basically think of a sort of a Pythagoras theorem, whereby all these are hypotenuse, and we can work it out what the adjacent side is going to be in relation to that hypotenuse. So in a sense, there's a few ways of getting it, and the way to get it when we do surface integrals, don't actually take that involved. Pythagoras theorem that we want to use. At this point, if I'm not going to start doing surface integrals right now, what's kind of going on there, or one way of looking at what's going on there, is there's a little bit of Pythagoras theorem where you're approximating your surface with lots of little blocks, and you're projecting those little blocks onto a horizontal surface, your xy plane, and you're ending up with a relationship between the area that's on the ground and the area of the actual surface, and that relationship is expressed with that square root over there. So at the moment, I'm essentially giving that to you without proof, because the proof takes a lecture. And I'm saving that for later. Question? Sorry, I'm... The partial derivatives exist, yes, and they're continuous. So it basically means my function is, well, it doesn't strictly mean that it's differentiable, does it? We've just been through lots of tortuous examples to show that it isn't necessarily the case. But from a purely mechanistic point of view, if we want to calculate that integral, it involves two derivatives, so we have to be able to work them out. So the derivatives have to exist. But fundamentally, what's behind that is it's saying that this process of projecting a piece of surface down onto the xy plane requires that, at the very least, my partial derivatives are continuous, if not the entire function being differentiable. Question?
No, I don't really understand what you mean by partial derivatives are continuous. Then the graph is continuous at the point you find the partial derivative.
The graph would have to be continuous because it's in order to be able to work out the... You're always able to find strange, weird cases that undermine any kind of general principle. So what is the... Nothing stricter than that. So continuity could actually, possibly your function isn't continuous. Possibly your function is not in fact differentiable everywhere. So it's actually quite a loose condition. It's quite a loose condition. All we want is that the partial derivatives themselves are continuous and exist. So we're not being particularly demanding on this piece of surface here. Okay, all right. But in fact, I now have spent 2 minutes talking about surface integrals, so let's go back to that. Okay, so I'm going to do, I'll do examples of surface area, but in fact, probably only mass and centers of mass. There are other courses where you're going to deal with centers of mass in a lot more detail than you are here. Statics probably is one of them. Physics, probably other courses I'm unfamiliar with. So here we're just kind of touching on it. But it is an application of double integrals. Just trying to think. In statics, do you not do any double integrals? You do moments though, don't you? Aren't moments double integrals? Is there not like some table at the back of the book where they say here are some typical moments and look how we got them by double integrals? Yeah? Of a plate or laminate area density, okay? Not volume density, this will be area density. The density of a plate or lamina is measured in units of mass density, because we're dealing with a two-dimensional object here. Okay, recall that now if your density is the same across your entire lamina, you could say density is mass over area. It varies across your lamina, so where density is a function of position on the lamina, your density is in fact oh, hold on, sorry, I did a page jump that I wasn't expecting. Sorry, I was at the bottom of the page and didn't even notice. There we go. Okay, so basically what we have here is we have density is different across your lamina. So density is a function of x and y. And so at any one point, there's a different density. So what we're going to do is we're going to chop our lamina up into lots of little pieces. Okay, and we're going to say there's a little delta mass for that little piece, and a little delta area for that little piece. And the density can be regarded at a point that's in the middle of that little piece can be regarded as the limit as the little piece shrinks and shrinks. So we're essentially approximating our density over lots of little blocks, yeah?
What type of density are you talking about? The density node is
Linear density. So it simply means that the density is mass per unit, per square centimeter, per square millimeter, per square inch. Now, in real life, it's hard to find things that are truly two-dimensional. And I suppose if you go right down to the atomic level, you could argue that nothing's ever two-dimensional. But you get things that we approximate as two-dimensional because their area is so what's the word? Sort of dominant over the thickness that we regard it as a two-dimensional object. There was a question in the middle here? Right, because I hadn't actually finished. I was going to leave a bigger gap there, but I'm at the bottom of the page, so I'll just do that. So mass is basically the sum. So what you're doing is you're saying, okay, we've got lots of little bits. We're going to approximate the density on each little bit, and we're going to add up. So then density is mass over area, so mass is density times area. Okay, so on each little bit, we're going to say each little bit's mass is the density of a point in the middle of that bit times by the area of the little bit. Of course, that'll just be an approximation, because if density truly does vary, then it's going to vary across each little block as well. But it'll only vary a little bit across each little block, so it's not too bad an approximation as long as the little bits are quite small. And then, of course, what integration does, integration says, okay, well, let's take this and let's push it to the extremes by allowing the little bits to shrink and shrink and shrink and shrink, and the number of them to become infinitely large. So that's what integration is. All integration is taking something, chopping it up into lots of little pieces, approximating something for each little piece, summing it all up, and then allowing the size of the pieces to shrink and the number of the pieces to become infinitely large. That's what all integration is. Okay, alrighty then. And then centers of mass. Centers of mass can be calculated. X bar and Y bar, where X bar is what we're essentially doing is we're weighting X coordinate. And for the Y center of mass, we're basically making the same calculation, but we are weighting it coordinate. So in a sense, it's almost like a weighted average, but it's like a continuous weighted average. I'm sure there are other courses that you will do that will go into this sort of stuff in a lot more detail. Where have you seen centers of mass? Statics? Physics? Physics? Anywhere else? I mean, there's lots of courses I don't know anything about. Civil, for instance, I've never been involved in anything in civil. Surely you must do centers of mass in civil. Only in statics. What about there's structures? And I'm running out of ideas of courses. Sorry, my background is maths. My background is in engineering. Anyway, centers of mass, clearly an important sort of thing. I'm sure you're going to stumble across them time and again. But for now, let's jump into an example. Number 12.
When you get this, how does this formula like make it
We're essentially weighting the density with the, if you look at the x, we're essentially weighting the density with the x coordinate, like a weighted average. So what's a weighted average? A weighted average is where something counts more than something else. So let's say class test 1 counted 3 times as much as class test 2. Which is desirable, because class test 1 is always easier than class test 2. In some hypothetical subject, let's say psychology 1. Okay, so in psychology 1, let's say class test 1 counts to essay 1. What do they do in psychology? Essay 1 counts 3 times as much as essay 2. Then the way you'd work out your weighted average is you'd take the 1 and the essay 1 and you'd multiply the mark by 3, and then you'd add it to the second one, and then you divide by 4, okay, because it's as if you had written 4 essays, but you've actually only written 2. That's a weighted average. And that's essentially what's happening there. We're basically working out the mass, but we're weighting the density with x. And then by dividing through by mass, we're basically removing mass from it, and we're ending up with just an x coordinate. So what we're ending up with there is information about x, but it's information about x that we have derived, resulted in, or obtained by a process of essentially doing a mass calculation. So it's your x coordinate weighted with the mass, or in another sense, it's your mass weighted with the x. So you're getting out your x center of mass. Question? This should give you? Yes. So you'll get a single value for x and you'll get a single value for y. Together they'll give you a point that you can actually draw as a dot in your diagram, and that dot is your center of mass. So you'll have your region which you can draw and you can color in, you can call it R, and you'll have a dot in your region which is your center of mass. And one way of thinking about it is if that's a laminar, if that's a stiff sheet of something, if you pick it up and you balance it on your finger, and you put your finger where the dot is, it'll balance because you put your finger at the center of mass. Okay, so that's an x coordinate and a y coordinate. And essentially what you're doing there is a continuous weighted average. Average is probably not the right word to be using there, but it's kind of what you're doing. X squared. Okay, that's a side parabola. Ooh, there we go. And y equals 0, that's the x-axis. So there we go. Okay, so that's the region. So that's a laminar. Okay, that's a two-dimensional sheet of something or other. And its density is just y. Let's work out the mass and the center of mass. The mass, come on, catch up with me, stylus. We're suddenly going to have two M's. Yes, there we go. The mass is double integral of density. Let me actually write without doing any thinking. You can write that. Okay? That is your basic formula for mass. Next line, I'm going to start plugging stuff in. Density is y. dA, let's have a look. dA. I'm going to do y first, and then x. Y goes from y equals 0 to y equals 9 minus x squared. For values of x that go from minus 3 to 3. I could as legitimately have done x first. X would have gone from the left edge to the right edge. The left edge is negative square root of 9 minus y, and the right edge is positive square root of 9 minus y. For values of y, they go from 0 to 9. But I'd rather avoid square roots. There's nothing wrong with them, but it's easier to work without them. But those are absolutely equivalent integrals. Equals, let's have a look. What did I differentiate with respect to y to get y? Half y squared. Let's plug 9 minus x squared into that. I'm going to be squaring it and then halving it. So that will be 81. You know what? I'm going to take the half out. I'm just going to take the half out. So it's going to be 81 minus 18x squared plus x to the power. X equals 81x minus 18 over 3 is 6 plus 5 minus 3. Pluggity plug plug, and you can see what's going to happen here. Can you? We're going to put 3 in, so we're going to get an 81 times 3, but later on we're going to get a subtract. 81 times much. So I was going to say it's all going to cancel out, but in fact it's the opposite. It's going to double. Everything's going to double. Because we're going to have an 81. Oh, come on, Stannis. Catch up with me, please. No. Good. I'm going to have an 81 times 3. I'm going to have a 6 times 3 cubed. I'm going to have a 6 times 3 times 5. And I'm going to have subtract. 81 times minus 3, plus 6 times minus 3 cubed, minus a fifth times minus 3 to the 5. Okay, and you can work those out, but see how they're going to double up. Because I have an 81 times 3, and I have a plus 81 times 3. The other have a minus, the other has also got a minus. And we're going to have a plus 1 and that is the fifth, and that's also going to be plus. So everything's doubling up. It's all electrical fractions, and it gives 129. No, we would not expect you to do that without a calculator. We will expect you to do simple stuff with fractions, but that's a bit hectic. I say there are 3 lectures altogether. 2 of us probably wouldn't expect you, and hopefully we can talk the other one round. Okay, now we need to do this. Well, of course there wasn't. My initial reaction seeing the 3 and the minus 3 was everything's going to cancel out. And then I realized actually no, it's not. But of course it's not going to cancel out. A massive 0, that would be very fishy. That would be very fishy. I would then think, I've made a mistake. Negative would be also very fishy. Okay, here is something. Here is something that you will want to take note of. Okay? If you do a calculation like this and you get a negative mass, and you look at it and you go, oh my goodness, that can't be right, and you look and you look and you look and you can't find the mistake, in a test or an exam, if you write, I can see that this is wrong, I can't find this mistake, I don't have time, I've got to move on, I will give you a mark for that. Because you are better than your friend sitting next to you who got negative mass and didn't even notice that this was a problem. Okay? So if you get a completely illogical answer, negative mass, negative volume, something like that, then chances are you've made a mistake. Either that or the people setting the question set a very stupid question that didn't actually work, which is a possibility, but we do try to avoid it. So if you get a completely illogical answer, but you can't find your error, write that down because it makes you better than the silly Billy who hasn't noticed. Yes. Not better. It makes you more observant of mathematical truths. Yes.
If we have a graph that goes we needed to involve different integers in order to positive number.
So the question was, if you have some sort of surface that ducks underneath the xy plane, and the question specifically asks you for volume, not just integral, but volume. Okay, we aren't doing volumes now, but later on we will. So triple integrals work out volume. But an equivalent thing here would be areas. What if you have? No, we can't do it with areas. No, we can in surface integrals again. Getting ahead of myself. But if you have something, if you're working out volume between a surface and the xy plane, and your surface goes underneath the xy plane, you'll need to chop your calculation up into several. I see what you say, using a double integral to work out volumes. Yes, no, quite. Yes, no, I agree with you. Yes. Volumes have to be positive. If your surface goes below the xy plane, a straight up double or triple, we'll be later doing triple integrals, won't give you the volume. So you have to chop it up, and the bits that are underneath you'll have to do separately and stick a minus sign in front of. Okay, all right. This is a very digressing. 1 over m double integral x density. So it's 1 over the mass double integral xy dy dx, y going from what was x0 to 9 minus x squared. Sorry, my handwriting is degrading here. The y center of mass will be very similar. Catch up with me, stylus. Yep. Y squared dy dx. Okay, all right, and then you work that out. Okay, you work that out, and now something interesting happens. Okay, because when we integrate the xy, we're going to get a half xy squared. Okay. And when we substitute that 9 minus x squared in, we're going to get exactly what we got before, only with an extra x everywhere. So we're going to get a half, whatever it was, 81, so it's 81x minus 18 x squared, so now it's 18x cubed. It was x to the 4, so now it's x to the 5. Now we really are going to have cancelling out when we get to the next strand. Sorry, I'm not into the sign anymore. I'm just going to have respect to x, and I'm getting, what am I getting? I'm getting, I'm dividing by 2, so it's 81 over 4x squared. But there's that. Sorry, this time I didn't take plus divide by 5, so it's 10. No, not 5, 6. Silly me. It's already a 5. Divide by 6, so 12. Okay, if I haven't done anything daft, then that's what you get. Now we really are going to have cancelling out. Because we'll have 81 over 4 times 3 squared, but later on we'll have minus 81 over 4 times minus 3 squared, but minus 3 squared is the same as 3 squared. So we're going to end up having cancelling out. You can plug all that in if you want, but everything's going to cancel out. We're going to have a thing plus a thing plus a thing minus the same 3 things. If you're not sure, leave a line blank and you'll see that you get x coordinate is 0. And I'm running out of time because basically it's the end of the lecture. I'm just going to give you this. Sorry, I understand it's the end of the lecture, but I want to finish off this problem. Okay, that's an integral. You can work it out. No great shakes. but I want to show you in the region. Let's go back to my picture. Woo. I can do better than that. Woo, maybe I can't. Here we go. Here's my parabola. Here's my region. My center of mass is all the way up there. X coordinates 0, Y coordinates almost 9. Think about how much that makes sense. Please keep quiet. I know it's about a minute over the end, but just think about how much that makes sense. My density, my region itself was symmetric. That's not enough to put the center of mass in the middle. It's the fact that my density was also symmetric. The density didn't care about X. The density was just equal to Y. So the density, as my Y got bigger, the density got bigger. As I move upward in Y through my lamina gets heavier. It gets heavier and heavier as it gets towards the top because it gets denser and denser towards the top. It makes complete sense that my center of mass is slap bang in the middle as far as X is concerned and right up near the top as far as Y is concerned. A center of mass somewhere towards the bottom or off to the sides wouldn't be nearly as logical, and a center of mass that's entirely outside the lamina would be incorrect, and you should really go and check the working. Okay, I like it if you draw your center of mass actually onto your drawing. Shows a little bit of understanding of what it is that you're doing, and let's begin. Okay, tomorrow we'll do questions.